Welcome back. So today our topic of discussion is going from the microcanonical to the canonical ensemble. Now it should be mentioned over here that in the thermodynamic limit both of them should give you the same result. So in the microcanonical ensemble what we had seen was this particular ensemble means that the system is completely isolated. There is no environment or a bath. In contrast, the canonical ensemble means the temperature is fixed. So that essentially this means that you have a system which is connected to a big large bath. You have allowed energy exchange with this bath, and that essentially means that the energy can fluctuate but the temperature is held constant, and that this temperature of the system is the temperature of the bath. Here of course we saw that the probability density of a microstate is equal to 1 over omega, where omega is the total number of microstates available. In this particular case we saw that the probability density for a system to be in a microstate with energy E goes as e to the power minus beta E, where beta is equal to 1 over kBt. Now the idea is now to build a connection between these two ensembles. For example, if you consider an ideal gas, which essentially in our picture the model system is n particles contained within the volume V and they're moving around, right? Now if that is the only system that is available to us, we will say that the system is isolated and we will apply microcanonical formalism to this system, determine the total number of microstate and therefore the rho, and from there we calculate the entropy and we calculate the rest of the thermodynamic quantities from this entropy. However, you can also argue, look, I have this big volume where I have all these particles which are moving around randomly. There is an underlying molecular chaos to this system, and I have treated the system in a microcanonical, using a microcanonical approach, because I don't have any additional information to me, just an ideal gas. But then if I zoom into the system, let's say I can consider this particle, the blue particle, which if I zoom out is part of the ideal gas, but if I zoom into the system I can see, oh, this blue particle is in a bath of other particles. Therefore I can, although it's a single particle level we are talking about, and statistical mechanics essentially single particle level is difficult, but we can still say that, look, but this particle is in a bath of the other particle. So in principle you can say that, look, I can pick up a subsystem sufficiently large enough which is in a bath of the rest of the system. So the idea is that there is a relation between a microcanonical and a canonical, and we are going to explore that. Unfortunately though, we need to know, to establish this connection, we have to know the explicit form of the Hamiltonian. So we will do it case by case. We'll take 3 examples and try to do it. So now microcanonical ensemble. So we'll start with the ideal gas example. Ideal gas. Here I have to determine omega of EVN, and this we have already done in a previous lecture. The total number of microstates that is available is 1 over h to the power n. I'm just considering in a one-dimensional system so that it's easier to handle. It's very easy to generalize such a thing. And then I have 2 pi n to the n by 2 gamma of n by 2 plus 1, and then I had twice me raised to the power n by 2. So this was the total number of microstates which were available. So total number of microstates available. And essentially this was integration of H, the Hamiltonian, dp1 dpn dq1 dqn, and our Hamiltonian for this ideal gas system was I equal to 1 to n pi square over twice n, right? So therefore from this omega now I can calculate this joint probability distribution, which is rho of, so we'll just write down this, is equal to 1 over omega, and this was the probability for the system to be in a microstate. This probability density, this is the probability density for the system to be in a given microstate. And essentially this statement is, this equation is telling me that all the microstates are equally probable because I don't have any other additional information. So the microstate is now defined by the set Pi Qi. So therefore you have a joint probability distribution P1 Q1, P2 Q2, all the way up to Pn Qn is given by this. Now from this joint probability distribution, when you say, look, I want to figure out this blue particle is in the path of the other particle. So essentially you are asking what is the probability density of finding the blue particle with a momentum P1 and at Q1. So rho P1, not, so okay, so not that. So what is the probability density for the blue particle to be in a microstate with P1 Q1? So therefore essentially this means that rho P1 Q1 dP1 dQ1 is the probability that the particle is, well, has momentum between P1 and P1 plus dP1 and is at, or not at, but is between Q1 and Q1 plus dQ1. This is the standard interpretation of probability density, and our task is to figure this out. So clearly I can now integrate out this joint probability distribution, because if you recall, if I have a joint probability distribution of n variables, this is my joint probability distribution of n variables, then essentially the probability distribution of a single variable is dx2 dxn. We will write down Pn to indicate that this is for n variable Pn of the set xi. Starting from this expression that I can determine the probability density of a single variable from the joint probability density of n variables by integrating out the other variables, I can write down the single probability density, single particle probability density rho 1 of P1 Q1 is going to be 1 over h integral dP2 dPn dQ2 dQn rho n of P1 P2 Pn Q1 Q2 Qn. Let me explain few things. I have included the 1 by h factorial purposefully here, because why should this 1 by h factorial be there? The 1 by h factorial is going to be there is because you are interested in, after all, the probability of finding this particle, the blue particle, within a momentum range of P1 and P1 plus dP1, and in between Q1 and Q1 plus dQ1, and this probability is P1 dP1 dQ1. But if you notice that if you do not have this 1 by h factorial, if you don't have this, then this quantity is dimension full. So in order to make everything consistent, you have to include the 1 by you have to divide this element by h, but that is unnecessary and is not what we learned in probability. So we include the 1 by h over here itself, and therefore this 1 by h comes. By the same argument, we are going to have h to the power n minus 1 over here, and the indistinguishability of these particles means that I am going to have n minus 1 factorial. Now this rho n is the rho that we had written down over here, which corresponded to this one, except that now I have brought in a subscript of n just to distinguish it from the fact that essentially this is an n particle joint probability this density you are looking at. The question now is that I am integrating over the momentum and the coordinates of all the rest of the particles. But what are the bounds? The bounds is given by Hamiltonian h is less than En minus 1. I have n particles which has so I have n particles with the total energy E. Now I have n minus 1 particles because I have taken out one of the particles, or I have tagged one of the particles which I am interested in, and therefore the system has an energy E of n minus 1, and I am integrating over all momenta and coordinates, which is of all the rest of the particles over a region which is bounded by this surface, which is h less than equal to En minus 1. So let's write this a little bit carefully. N minus 1, and I have an n minus 1 factorial. When we did it for the n particle system, we had this as h of less than equal to En, which is essentially this one, right? Now let's plug in the value of rho n. So rho 1 of P1 Q1 is going to be 1 over h dP2 dP all the way up to dPn dQ2 dQn divided by n minus 1 factorial h to the power n minus 1, but rho n is 1 over integral h less than equal to E, and here I have h less than equal to E of n minus 1, and dP1, all the momenta and coordinates are being integrated over, right? So which means I have this very nice expression as 1 over h less than equal to En minus 1 dP2 dPn dQ2 dQn divided by h less than equal to E dP1 dPn dQ1 dQn, and this I can write down as omega, total number of microstates with an available energy of En minus 1 divided by omega En. So if you are careful enough, one also has to write down V of n minus 1, and we will write down this as E of Vn. So let's write down, I know the expression for omega EVN, so we will rewrite it over here. Omega V EVN was twice pi raised to the power n by 2 gamma of n by 2 plus 1, and I had 1 over h to the power n, 1 over n factorial, and I had twice me raised to the power n by 2. It follows that I have omega of En minus 1, Vn minus 1, n minus 1, there has to be a v to the power n here, is going to be 1 over h to the power n minus 1, 1 over n minus 1 factorial, twice pi raised to the power n minus 1 by 2, gamma n minus 1 by 2 plus 1. And then I'm going to have twice me n minus 1 raised to the power n minus 1 by 2, and I'm going to have v to the power n minus 1. Because you are integrating over this momenta q2 to qn, and all of these can individually will give you a value v. Therefore, you have n minus 1 such variables, so this gives you v to the power n minus 1. So the ratio then becomes e of n minus 1, v of n minus 1, and I have n minus 1 particles to the ratio of, to the value of omega of evn is 1 over h to the power n minus 1, 1 over n minus 1 factorial, twice pi n minus 1 by 2. I'm sorry, there is an alarm which is sounding now and I have no idea why, but please bear with this noise. Hopefully I'm audible over this noise. And then I have twice me n minus 1 raised to the power n minus 1 by 2, v to the power n minus 1. Now I have this. I have 2 pi n by 2, 2 pi raised to the power n over 2, twice me raised to the power n by 2, v to the power n, and the numerator will have h to the power n, 1 over n, it's going to be n factorial in the numerator, and then I'm going to have gamma of n by 2 plus 1. Let's collect these terms together. That I have h to the power n, h to the power n minus 1, n factorial, n minus 1 factorial. The 2 gets cancelled out, so that I have pi to the power n minus 1 by 2 divided by pi to the power n by 2. I'm going to have gamma of n by 2 plus 1, gamma of n minus 1 by 2 plus 1, and then I'm going to have v to the power n minus 1, v to the power n, twice me n minus 1 raised to the power n minus 1 by 2 divided by twice me raised to the power n by 2. This part gives me an h, and this part, assuming that n is in the thermodynamic limit, n minus 1 is equal to n, gives me a unity factor. This one gives me a 1 over square root pi. Using the same limit of this, n minus 1 is approximately going to be n. Using Stirling's formula, for large enough n, this is going to be n by 2 raised to the power half, and this gives me a factor 1 by v. This is what I have to determine. So let's just collect all these terms together. This gives me h, and this is over square root pi, and then I have n by 2 raised to the power half, 1 over v, twice me n minus 1 raised to the power n minus 1 by 2, and twice me raised to the power n by 2. Now, the conservation of energy tells me that E is going to be P1 square over twice m plus P2 square over twice m all the way up to Pn square over twice m. So this is essentially P1 square over twice m plus sum of I is equal to 2 to n pi square over twice m. You immediately realize that this is the term, the first term is the energy of the first particle, whereas this is the energy of the rest n minus 1 particles. So essentially this is equal to E of n minus 1. So hence we write E of n minus 1 as E minus P1 square over twice m. So this pen is behaving a little erratic. So that the ratio of the two phase space volumes En minus 1, Vn minus 1, n minus 1 divided by omega of E, V and n is going to be h over square root pi n by 2 raised to the power half 1 over V, and then I have twice m of E minus P1 square over twice m raised to the power n minus 1 over 2 divided by twice me raised to the power n by 2. Let's take the twice m inside the bracket, so that this gives me h over square root pi n by 2 raised to the power half 1 by v twice me minus p1 square raised to the power n minus 1 by 2 divided by twice me raised to the power n by 2. What I'm going to do is I'm going to take out a factor of twice me in the denominator raised to the power half and rewrite them as twice me minus p1 square raised to the power n minus 1 over 2. Now here is a word of caution that in this case, in this step, here itself I could have said that look, n minus 1 is approximately n, correct? But that would have given you a wrong result. You can go ahead with this approximation here itself in this step, and you will see that you will arrive at a wrong expression for this rho single particle probability density. So one has to be very, very careful where you are taking the limit, how you are taking the limit. Coming back to this, I have h over square root pi. Let's take all the quantities within the square root together. So I have h divided by v, and then I have n. This 2 and this 2 gives me a 4. There's a pi over here, so this is 4 pi m times e raised to the power half, and then I have 1 minus p1 square divided by twice me. This is raised to the power n minus 1 by 2, and here I make the approximation. N minus 1 by 2 is approximately n by 2, so that I have this result. Now clearly from this expression, if we want to move ahead, we have to see that I know that the energy is an extensive quantity, therefore E would scale with n. So the denominator is a very large number because I'm looking in large system. So therefore this inverse of this twice me inverse is a very small number. Consequently, what I can take this expression 1 minus this, and I can replace it by the exponential p1 square over twice me, because this this expression that we have over here is essentially, it looks like the Taylor expansion, the first two terms of the Taylor expansion of this exponential. So that this becomes h over n divided by 4 pi m times e raised to the power half e to the power minus p1 square over twice me raised to the power n by 2, and this I can nicely write down as, why did it there, sorry, this has to be h over v n divided by 4 pi me raised to the power half e to the power minus n p1 square over twice me, and this is the ratio of e n minus 1 v n minus 1 n minus 1 divided by omega of e v n. Now the single particle probability density rho 1 of p1 q1 is given by 1 by h times omega of en minus 1 vn minus 1 n minus 1 omega of e v and n. So this 1 by this h cancels with this h over here, and we have this nice expression which is n over 4 pi me raised to the power half e to the power minus n p1 square over twice me. Clearly, it is a nice expression but not very familiar. For that, we substitute E. I know that for an ideal gas in one dimension, the energy of the gas is given by E is equal to n by 2 kBT. So that rho 1 P1 Q1 is 1 by V 4 pi m n by 2 n by 2 kBT times n raised to the power half, and then I have e to the power minus n p1 square. This has to be 4 because this is raised to the power n by 2. This has to be 4 here, so this is going to be 4 m n by 2 kBT. There are cancellations. This gives me 2. This n and this n cancels out. Similarly here also this gives me 2, and this n cancels out, so that I have 1 over v 1 over square root 2 pi m kBT e to the power minus p1 square over twice m kBT. If you write down beta is equal to 1 over kBT, then this quantity is 1 over v square root beta over 2m pi e to the power minus beta p1 square over twice m rho 1 of p1 q1. Now you see that this distribution is the canonical distribution. So starting from the microcanonical ensemble, we have shown explicitly that your canonical distribution function follows if you consider one subsystem, one part of the subsystem, to be in the bath, to be immersed, as if it's immersed in the bath of the rest of the system. I have determined the single particle probability density. Of course, one can do 2 particle, 3 particle, and one should get a sum over the momenta here. This number, so I have treated one single particle as a subsystem which is moving in the bath of the rest of the system. One can in principle take a subset of these momentas as part of the subsystem, and you will see that you are going to get the canonical distribution. Since P1 and Q1 is nothing special, because the particles are indistinguishable, the single particle probability density rho PQ is going to be 1 over beta over 2m pi e to the power minus beta p square over twice m. If you really now say that, look, I am not worried about the coordinates, I can, from this is also a joint probability distribution of P and Q. If I just want to know the probability distribution of the momenta, rho P is integral rho 1 pq dq, which is rho 1 pq. This part does not depend on the coordinates, and therefore you have a dq, which is v times rho 1 pq, and then this v factor will cancel with this v factor, and you are going to come up with the Maxwell's Boltzmann distribution twice m pi e to the power minus beta p square over twice m.